In this video we show how data transformations can be a very useful way for improving statistical models. More specifically, in cases where the available parametric distributions such as Gaussian distributions or student t distributions cannot provide a close fit to the observed histograms, data transformations might actually be an outcome. In the example, we have time measurements from a Fitts law experiment with 9 conditions. And by definition, time measurements are always positive, which is a reason why a lot of researchers first transform their time measurements by a logarithmic transformation actually before performing statistical analysis on it. We will look at data transformations in a more systematic way and use multi-model comparison to actually decide which data transformation to use. Standard advice in statistics when the observed histograms, like in this case, don't match closely to the Gaussian distributions is to use rank order distributions. But so let's first change the distribution to student t in order to make sure that outliers don't have a very high influence on our data. So if we apply a rank order transformation on the data, we will see that if we go to that the AAC actually goes up by quite a bit. So there's actually no evidence for a rank order transformation in this case. So let's switch it off again and start from scratch just to make sure that we know what we're doing. So one class of transformation that ILLMO supports next to the rank order transformations is so-called spline functions. They're monotonic smooth functions that can be used to transform the data. So the data is actually being transformed by this spline function, and the transformed data is approximated by Gaussian distribution or student t distributions in this case, rather than the original data. This is equivalent to saying that the student t distributions are actually mapped by the inverse of this function to create distributions which are changing in shape. So in that creates a lot more flexibility, as you can see here in this example. And the fact that that is an improvement is indeed also confirmed by the decrease in AIC. So if we look at the maximum likelihood statistics, we see a very high evidence ratio in favor of this spline transformation. Now the first parameter that we see here for the spline transformation is the difference in slope between the minimum and maximum value. We can create additional parameters, meaning internal knot points, and to see what happens, you can see that we can further decrease the AIC, so get an even improved fit. So we can have 2 knot points. And then it starts to saturate, so basically meaning that there's probably no use in having more knot points. So we can look at the weights, and we see obviously that the last model has the biggest weight, followed by the model with 1 internal knot point and very little weight for evidence. For the other 2 models, no transformation or a very simple spline transformation. So let's put it back to linear and have a look at the second class of functions that are being supported by ILLMO. These are so-called box-Cox functions, which are power law-like functions. So we can actually create a logarithmic transformation by having an exponent by a box-Cox power of 0, and we can have an offset value of 100. So that creates a function that is even with an even lower AIC and a much higher weight even in the spline functions. We can go even one step further and make this power into a variable. See that the LLC goes down slightly, but since there's one more parameter, the AIC goes down and hence also the weight for it. So there's very little evidence for having a value different from 0, different from a logarithmic function, which we can also see by creating the log likelihood function and log likelihood profile for that power law, which shows that the confidence interval clearly includes 0.